C was pre-multiply A, the original quadratic form, by the transpose of the matrix, pre-multiply by the transpose of the matrix of eigenvectors, and post-multiply by the matrix. So I said, let's put, again, because I didn't want to do everything by hand, I said, let's put the eigenvectors in this thing we'll call V. Eigenvex is a simple command line for MathCAD. It understands that this is an executable. And eigenvex says, go find the eigenvectors of A cubed. Because oh, by the way, as some of you discovered in the very first assignment that you did, software often has reserved words and reserved letters. MathCAD, because it's built for engineers, has lots and lots of reserved words and letters. And engineers, of course, are very concerned about units, like feet and degrees Celsius and stuff like that. So the reason I use AQ here as the symbol for the quadratic form that I gave you is because big A is a reserved letter in MathCAD for angstroms. Okay? And in order to make sure that you're not confusing MathCAD, it's a good idea not to use their reserved letters and words and things like that. And the way you tell whether or not the character is reserved is if you, for example, if I had just said A was equal to something, it would underline big A with a green wiggle line, and that tells me that that character is reserved, and I'm changing the definition that they had reserved for that. And you don't want to do that, because sometimes you can confuse things. You think you're working with one number, and they think you're working with another, and it just makes a mess later on. So it's a good idea to stay away from things. So B does what you were supposed to do. B was pre-multiply by the transpose of the matrix of eigenvectors, and post-multiply by the matrix of eigenvectors, and lo and behold, what do you get? But a matrix B that has the characteristic roots on the main diagonal. And then the last part, of course, is simple. Now find another matrix L, such that when you pre-multiply B by L and post-multiply B by L, you get an identity matrix. So all you need is, on the main diagonal of L, 1 over the square roots of the characteristic roots, and zeros elsewhere. And you're done. So the hard part was, the question was ABC. By the time you got to B, that was a walk in the park. Before I let you ask a question, let me tell you what the point values for the questions were. You ask your question. It's going to take me a little longer than I thought.
I just wonder, eigenvectors are always served by definition for length?
Yes. 1A was worth 4 points. 1B was worth 4 points. 1C was worth 4 points. Question 2 was worth 10 points. Question 3 was worth 10 points. 4A was worth 10 points. 4B was worth 15. 4C was worth 5, because that was just simple arithmetic. C. And D was worth 4, because there was no mental gymnastics. There shouldn't have been any mental gymnastics involved in D. Question 5. 5A was worth 2. 5B was worth 8. 5C, D, E, and F were each worth 5. And I tried to assign points on the basis of the degree of difficulty. If you had to remember a lot and do a lot of work to figure something out, then it was worth more points. So question 5, data for the model y is equal to A0 plus A1 times x1 plus A2 times x2 yields the following. X transpose X is that 3 by 3 matrix. X transpose Y is that 3 by 1 column vector, and it also says that the sum of square deviations of Y around its mean is 150. So how do you interpret X transpose X? Well, the first, you have the model up there. Y is equal to X. We'll call it alpha plus U. Plus U. Okay, that was the model we started with, although it was written in the exam as A0. A0 plus A1 x1 plus A2 x2 plus fewer. So as we look at these, x consists of, let's let little l represent the intercept, and x1 and x2. Okay, and I put a little superscript 1 and 2 there because this represents a column. What entries are in the column labeled little l? Any wild guesses? Ones. Ones all the way down the column. And of course, the next column has the set of observations on the first variable in it. And the next column has the set of observations on x2. So that's x. So when you take the transpose of x, you swap the rows for the column. You take the first column and make it the first row. Take the second column, make it the second row. Take the third column, make it the third row. So if that's x, then x transpose must be a row of ones, and then a row that has in it okay, so now you see that the interpretation of the subscripts were preserved when I did the transpose. Here, when I wrote down x, the first subscript denoted the row position, and the second subscript denoted the column position, and that's convention. Any linear algebra book that you pick up in the world, that's going to be the convention. And so this is the nth row of the first variable. This is the nth row of the second variable. So then we have, as the third row, you have x12, x22, all the way out to xn2. And I preserved the subscripts. I preserved the subscript meaning so that we would know that the last entry on the third row is the final observation on the second variable. So when you do that multiplication, we're going to get a 3 by 3 matrix. In the row 1 column position, you have that row multiplied by that column, which is the sum of 1 from 1 to n, where n is the number of observations we have. And then you have this column times that row, and then add them up. So this is the sum of the xi1 from I equal 1 to n. And then we have the sum from I equal 1 to n of xi2. And because x transpose x has to be symmetric, right away I can write down xi1, I equal 1 to n, sum of the xi2, I equal 1 to n. And then on the main diagonal, I get the own squares. On the off diagonal, I get the cross products between xi1, xi2,